Okay, thanks for the invitation. Thanks for the introduction. And so the motivation to have a talk like this, where part of it is the early universe, part of it is the Milky Way, also has to do with the fact that a number of us have been here for the last few days. I mean, the first part in New York, the second part here at the Institute, to discuss inflation. And I'm not going to really walk you through it. I was just going to use it to point here when I say inflation. But so there's a number, even though the theory is quite well developed, there's still a large number of pretty basic open questions. So for example, we don't know what the energy scale of inflation is. We don't know how far the inflaton traveled. I'm not introducing all these terms because I think people have heard them before, so I don't want to bore you with the little model of the ball rolling down the hill and so on. We also don't really know if there's any additional light degrees of freedom, if there's just the inflaton, what's the propagation speed of the inflaton quanta, all relatively basic things that you might ask about. We're not really sure exactly how it began. And another thing that we've been thinking about here at the workshop, or some of us have been giving nice talks about, is how do we actually calculate observables more efficiently. And a lot of these things I think are interesting just in their own right from a theoretical point of view. But what makes it exciting is that we actually think that we have a handle on them and might learn something about them in the next few years from observations. So for example, if you're interested in the energy scale of inflation or how far the inflaton traveled, you might hope that we get some insights into that from observations of the cosmic microwave background, and in particular contributions of tensor modes to the cosmic microwave background. You might also hope to learn something about these things from looking at non-Gaussianities, not so much in the cosmic microwave background, because we only expect an improvement over the bounds that we have now by a factor of 2 or so, even though there's more to be said, because that doesn't really include all shapes. Not everything necessarily has been looked for, so there's some room there. But for the most part, it's coming for, or one would hope that one can get improvements from upcoming large-scale structure surveys. What I'll be focusing on in this talk is the observations of the cosmic microwave background and the observations or attempts to measure the imprint of primordial gravitational waves in the cosmic microwave background. And also here I won't say a whole lot about it because I'm sure you've heard some of these things many times. But the basic upshot is that if you detect primordial gravitational waves in the cosmic microwave background, or the imprint on the polarization of the cosmic microwave background, what you would learn is roughly what the energy scale or the expansion rate during inflation is of the universe, and through the Friedmann equation what the energy scale is. And you would also learn, for if we detected with experiments that we can conceive doing in the next few years, that the inflaton traversed a Planckian field range. So here I'm not necessarily too specific about it being bigger than 1 in Planck or 0.8 in Planck, 0.5 in Planck. It's all the same to me, especially because we know that gravity is not really a UV complete, or GR is not really a UV complete theory. If the UV completion is somehow weakly coupled, there should be scales that are parametrically below the Planck scale. And so a lot of these discussions apply even if it's not necessarily super Planckian, but around the Planck scale, because these displacements, you don't expect them in a generic low energy effective field theory. And so the idea is that these kind of observations would teach us about some things of quantum gravity. They also teach you additional things. They tell you interesting things about axions, about moduli, about a number of other things. And it's really hard to overstate how exciting a detection of these gravitational waves from the early universe would be. And to some extent, we already had that experiment and saw that everyone got excited about it because there was a claimed detection by the BICEP2 collaboration where the E-modes that were seen were consistent with the E-modes expected from simulations. The B-modes were larger than those that were expected based on naive simulations that didn't properly take into account foregrounds. So we now know that what we have here is a nice map of dust, not really primordial gravitational waves. Now you might be disappointed about it, but at the same time, it's still useful information if you want to move forward and constrain more tightly the contribution from gravitational waves, because you can use this data to clean the dust place upper limits on the tensor to scalar ratio. And the current bound we have is that the tensor to scalar ratio, so the ratio of power in gravitational waves to power in scalar or density perturbations, is less than 0.064 at 95% confidence level, and this number won't really stay there for long, so it'll move downward pretty rapidly, because there's a lot of experiments taking data right now, and also a lot of experiments planned and taking data soon. So I'll briefly show you some of them, because the question as to where we can get to on what time scale came up in the workshop a few times, so maybe it's helpful for some people to see it. So the stage 2 is where we are now. These are the experiments that most of you, I think, also know and love or hate, one or the other, I don't know. So there's the BICEP experiment that I was mentioning. There's SPT, Spider, people here obviously very familiar with. There's Polar Bear, Advanced ACT, there's ABS, CLASS, EBEX, a number of experiments that are taking data or should come out with results soon. Then as you move into the not too distant future, there's what people usually refer to as stage 3. And stage 3, my slide is a little bit misleading, because my slide is about the Simons Observatory. Stage 3 is really more than that. It's just everything that comes beyond stage 2. One of the examples, sometimes people call Simons Observatory stage 3.5, but I mean, this is one of the stage 3 experiments, which really brings together groups from different collaborations, from Polar Bear, Simons Array, the ACT collaboration. So you see there's going to be an experiment in the Atacama Desert where these were. Another experiment, well, let me first, so here show you the expected sensitivity of Simons Observatory from a paper that was recently appeared on the archive. And you see, I'm not really going to discuss the details, I mean, what the different foreground models are, but if people have questions, I'm happy to talk more about it. But the basic upshot is that you expect to get to sigma r of 2 to 3 times 10 to the minus 3. So that's on the time scale where the telescopes are supposed to be taking data or start taking data, first light in, let's say, 2 years from now in 2020. And then you might have this kind of thing in maybe 4 or 5 years after that, because it takes a while to take all the data, to analyze it. But this is roughly what you expect to get to with this experiment. And then there's another set of experiments, the continuation of the BICEP experiment, which will also then collaborate with SPT3G to do the delensing. And here there's a slightly different plot I'm showing you, has slightly different information, so it depends on exactly what you want to see. But here the existing measurements are the BKP paper, the BK14 paper, and the gray curve are the forecasts. So one of the things you see is that the forecasts match with the measurements, which is not too surprising because they're at some level based on these, and the extrapolation isn't too bold at this point. You also see at what time there's which frequencies. You also see that there was a BK15 here, which is supposed to come out any time, but it has been supposed to come out any time for about a year now or so, I would say. In any case, the uncertainties that you should expect from the upcoming paper is about sigma r of 2 times 10 to the minus 2. And then you can see as you go to the future, to the area where we were looking at the Simons Observatory, also here you get to a few times 10 to the minus 3 in that set of experiments. So that's roughly the goal for the stage 3 experiments, a few times 10 to the minus 3 for sigma r. If you want to go further, go lower in R, it takes a bigger effort. So this is illustrated here. It really takes the entire USCMB community coming together, working on one big experiment. That's the experiment that's been referred to as CMB-S4. There was a discussion if it should be renamed because it's not a very inspirational name, but everyone's used to it by now, so the decision was it should just be CMB-S4. There may also be additional missions from space in this time frame. One of them is a Japanese mission, Lightbird, and there's also a NASA probe study, although I put it in parentheses because it's not really a proposal or anything, it's just part of the decadal process where the question isn't should there be this CMB mission, but should there be missions with a price tag of just below $1 billion. And so even if everything goes well, I think the best possible outcome would be just that there's this line of NASA missions.
If I may ask, that effort to the next generation assumes that the previous results will not be successful. That is, we won't detect an R. Or would these experiments still be exciting even if there's a detection of a positive value of R from over the next 10 years?
For me, it would be exciting. I mean, if you see something, then I think there's even better motivation to actually go after it, measure it, characterize it. So I think if you see something, we're in much less trouble than if we don't see anything, because eventually you're starting to wonder if you're eventually going to see something. So for me, if you see something, there's good motivation to go ahead and really try to characterize the signal. At the same time, you should also keep in mind that while the talk is focused on primordial gravitational waves, these experiments really do a lot more than just look for primordial gravitational waves. I have some slide that also doesn't do it justice, but you can also measure the effective relativistic degrees of freedom, or number of effective relativistic degrees of freedom, the neutrino mass. There's a lot of information about structure formation, baryonic feedback, astrophysics. I mean, there's a lot more that you can do with these experiments. It isn't just primordial gravitational waves, even though I'm focused on that for now. But it'll be a bit clearer maybe in a second. This is just there to illustrate that it's really an effort of the entire CMB community. So there's big groups meeting on a very regular basis. I eventually stopped doing it because it doesn't all fit here. It's every half year or so. There's a CMB-S4 science book if you want to take a look. We also spent a lot of time on another report for the DOE and NSF, the CDT report, where there's updated simulations, forecasts, and so on. The upshot is, I think, that CMB-S4 will be a single experiment and one collaboration that's operating telescopes at two different sites, the South Pole and the Atacama Desert. Sometimes there's some discussion of having a third site in the northern hemisphere just so you can cover the full sky, but it's not really been too serious of a debate at this point. So right now, I think the main discussion is having telescopes at in Antarctica and in the Atacama Desert. And the survey is broken up into really two separate pieces. One piece is a deep survey on a relatively small patch to go after the primordial gravitational wave signal. And then there's a wide survey where you're trying to measure or map as much of the sky as you can use, as much of the sky as you can see from Chile, and as much of the sky as you can use, given that there's foregrounds, to measure things like the effective number of relativistic degrees of freedom. And here the uncertainty that you can expect is something like a sensitivity at 2 sigma of around 0.06, and I can explain, if anyone is interested, why that's an interesting target. You can try to measure the sum of the neutrino mass, growth of structure, and so on. This is all coming from the wide survey. So there's a number of small telescopes and one big telescope to do delensing for this part. And then there is large, 6-meter telescopes, 2 or 3 depending, for the wide survey. And the goal, again, for primordial gravitational waves, there's more to be said about the other science goals, is to get a robust detection of primordial gravitational waves, or an upper limit that says that R is less than 10 to the minus 3 at 95% confidence level. So this is the kind of numbers that you can get to with CMB stage 4. And at first sight, usually when people first present you measurement of B-modes, it's presented as a statement that it's somehow straightforward because at linear order, scalar perturbations don't generate them. So if you see them, you right away know that what you saw are primordial gravitational waves. That's not really true for a number of reasons, but I mean, one obvious reason is just that weak gravitational lensing of the CMB. So the CMB passing on its way to us gets lensed by large-scale structure. This converts E modes into B modes and gives you a signal that you have to fight if you're trying to dig out the primordial gravitational wave contribution. And then, as we saw from the BICEP example, galactic foregrounds also generate B modes. So so the big challenge is if you look at it, you can either look at it at the map level or you can look at it at the power spectrum level. Here I'm showing you, if assuming you have maps from CMBS4, what it would roughly look like and what the challenge is, what you're trying to achieve with them. So here are the spectra that you measure from simulations at 30 gigahertz, 40 gigahertz, and so on. So you see it's going down to 85 gigahertz and then back up as you increase in frequency because it's dominated by synchrotron and is bright at low frequencies. Then there's a minimum somewhere. We'll have another plot to illustrate that. And then it goes back up because you're looking at the dust, but you see that everything here is significantly above the signal. And this is really the signal in the absence of a gravitational wave contribution. And so the goal is to use these kind of spectra to tell the difference between these two things at 5 sigma. So that's the goal. And it doesn't seem like obviously possible or trivial. So you have to really measure this with high signal to noise to do this. It's a little bit better than what it looked like because you can remove, by doing measurements on small scales, that's usually referred to as delensing, you can remove some of the lensing contribution. So it makes the problem better because it moves this down. And then the difference between the delensed spectra with R equals 0 and 0.03 is a little bit better, but you still see that you're buried below the foreground. So clearly, the biggest caveat to any of the forecasts you see and statements of what you can get to is our limited understanding of foregrounds, really. And this is a plot that just highlights that. So as I said, the upper limit right now is, let's say, less than 0.06 at 95% confidence level. And so even if you're only interested, let's say, in a signal at 10 to the minus 2, you see that it's always below synchrotron and dust, even in the brightest in the cleanest regions of the sky. So you can't really avoid the foregrounds. You might have hoped that you can somehow get around it. I mean, that was the idea at some point. You just get around it by measuring very clean parts of the sky. But obviously, that's not really an option. So there's either the dust or the synchrotron, or both are always brighter than the signal you're looking for. And so you can't really get around dealing with the foregrounds, and you have to also have some understanding of the foregrounds when you're designing the experiments. So it's a little bit of a cartoon, but the basic upshot is that in polarization, the things you're looking at are dust and synchrotron, and then the question is, how do you model them, or what do we actually use? Not what you would necessarily use, but what the CMB community right now is using. And there's a number of different approaches. The most widely used approach until recently, or still, I think, is an approach that is based on templates from existing experiments like WMAP and Planck. And so here the idea is that you take a template either from WMAP 23 gigahertz or LFI 30 gigahertz as a template for the synchrotron, and you take a map of the polarized emission at high frequencies, in this case Planck 353 gigahertz, as a template for the dust, and then make up some spectral dependence and interpolate between them to make a prediction what the foregrounds look like at different frequencies. And obviously, there's some issues with that in the sense that if we had maps that are good enough for the future experiments, we wouldn't be doing the future experiments. So in other words, these maps have instrumental noise in them that you somehow have to deal with. You want to get rid of them. So typically, you smooth it. On larger scales, the signal is brighter than the noise, so you smooth it. But then you lost the resolution, and you somehow have to put the small scales back. And typically, what's done is you just populate it with some Gaussian random fluctuations. But as we'll see, this is not really, I mean, I think it's clear to everyone, this is not really what dust and synchrotron actually looks like. And this has some effect on the measurements, but also in principle on techniques that you might use to disentangle the signal from the foregrounds, because we do think that the signal is highly Gaussian. So another way to show that these templates don't really look like the real sky, this is because you're just populating the small scales in some random way, is by showing you a histogram of the polarization fraction. So you just take the maps of Planck or the sky models, and you measure the polarization fraction, which is just the ratio of the polarized intensity divided by the total intensity, and you make a histogram of it. The orange curve is what the Planck data looks like, and this is what various models look like. And you see they don't really in any way resemble the histogram of polarization fractions in the sky. And there's also many other ways that they just don't look like the real sky. So somehow we have to do better than this, and that's what I'll be talking about in the rest of the talk. So one interesting approach that Susan Clark and also Colin are the experts on, so you can ask them if you have questions about it, is to use H1 observations to predict both the amplitude and the polarization angles. Using the amplitude to predict CLBB or EE, that was used for a while. The new step is that you can also use the data to predict the polarization angles, and then you assume that you have a constant dust-to-gas ratio, assume some spectral dependence or composition of the dust, and make maps that you can use as a model. Another approach that we've been working on recently is based on MHD simulations. So you try to simulate the ISM, and again, in the simulations, so this is a snapshot from one of the simulations, you don't really, at this point, we're not including dust. This is just an MHD simulation where the density is just measuring the density of H1. And after that, you again assume that everything is well mixed and assume a constant dust-to-gas ratio. Strictly speaking, there's capabilities where you could trace some of the dust particles, but we haven't really been exploring that or whether it really works. So, I mean, and then for this is what you can do for the dust. Again, you also assume a spectral dependence if you want to make predictions at different frequencies. For electrons, it's a little bit more difficult. So you can certainly use the observed energy spectrum from something like Pamela, and that also correctly predicts the frequency scaling of the synchrotron radiation. But we don't have cosmic rays in these simulations, at least. So the density of electrons we included in a very heuristic way. So this is really just a starting point. So I'm not saying that this is replacing everything, but I think there's some interesting lessons from the simulations we've been looking at that I just wanted to share. It's all very preliminary, but I thought maybe some people find it interesting. So one thing, so these simulations, I'll say it again later, but these simulations, these were simulations that already existed before Planck took any data. So they're not in any way fit to the Planck data or anything like this. The only reason I started looking at them is because when I was visiting San Diego, I was talking to Alexei Kritsuk, asked him what he's working on. He says, oh, I'm doing simulations of the ISM, and he's was very excited about them. So I asked, well, can we try to use them to see what this looks like if we make a map of dust and synchrotron from them? Does it in any way look like the Planck data? And to me, it looks remarkably like the Planck data. So you just take these cubes that really were not designed even for the kind of regions of the sky that we're interested in. So here the question they were studying were molecular clouds, star formation. So it's not really targeted at the high latitude regions that we're interested in. So I just took them and based on a simple model that I'll describe in a little bit more detail. I mean, you can measure the power spectra, and it correctly reproduces the E to B ratio that I'll also say a little bit more about. That was interesting in, well, it caused a lot of excitement in Planck. It's a bit surprising because the same was seen in WMAP, so I'm not sure why it was more exciting later on. But anyway, so there's an asymmetry in power between B modes in red and E modes in blue. It also correctly predicts the TE correlations and the scale dependence. So if you measure the slope, it's consistent with what's seen in the Planck data. And this to me was kind of interesting, and I think suggests it's worth looking at more. Now, from my point of view, for the most part, the foregrounds are somewhat of a nuisance that we're trying to get rid of when we're measuring the cosmic microwave background or looking for signals from the early universe. But of course, there's more to it than that. There's really interesting physics that you can learn, as people here know very well. So from the frequency dependence, you might be able to disentangle or learn about what the composition of the dust is. You can use these observations to measure as one way to measure the structure of the magnetic field of the Milky Way. And as I'll argue, you can use them to really study the structure and statistics of interstellar turbulence. So that's mostly what the Planck data seems to be about. And it's interesting for many astrophysical processes, as everyone knows. And it's also, I think, just fascinating in its own right to understand MHD turbulence better in this regime. I mean, it's in a regime where there isn't all that much known. So the diagnostics, I think one can improve, and you can really make contact in ways where you're not just looking at the observables that people in the CMB are looking at anyway, but the diagnostics that people have been looking at are things like the B to E ratio. Before, it was always the E to B ratio, and it was 2. Planck somehow made it the B to E ratio, and it's now 0.5. But the asymmetry is the same, so you see that there's about a half the power in B modes as there is in E modes. It varies a little bit depending on where you look. I took the figure from the old Planck paper because somehow the updated measurements are there in the new papers, but there isn't really a figure. The scale dependence is another characteristic. So you look at the power spectrum, you measure the scale dependence. This is just for different masks that were used in the analyses. And you see that the spectral index, or the slope for the CLs, is something like, goes like L to the minus 2.4 to L to the minus 2.5. And so that's a number that you might want to remember, because I'm not necessarily showing this figure again, but so just remember the minus 2.4 and minus 2.5 when we're looking at the simulations. And another diagnostic you can use is the histogram of the polarization fraction that I was already showing you. So this is the histogram as measured from the Planck data by the Planck collaboration, and this is something that you can use to compare your foreground model to. Here, this is, I think most people are familiar with it, so I won't really say much about it, but what we're using for the simulations are the MHD equations. So you're describing the medium on large distances, large compared to the other typical distance scales like the mean free path, Larmor radius, and so on. And the equations are just mass conservation, momentum conservation, energy conservation, and the behavior. So these are some numbers that I'll just show you to get you an idea what regime the simulations are describing. Are the sonic Mach number is familiar to everyone. The Alfvén Mach number is the ratio of the fluid velocity and the Alfvén speed, which for now is easier to think of intuitively, I think, until I say a little bit more about the modes. It's easiest to think of as just the square root. I mean, you could have as well defined m squared, but it's the square root of the ratio of the kinetic energy in the medium divided by the kinetic energy in the magnetic field. And then there's also the parameter, which is usually referred to as plasma beta, which is just the ratio of the pressure in the thermal pressure in the medium and the magnetic pressure. So these are some of the numbers that will come up when we're discussing the solutions, the simulations. And for the simulations I'm discussing, there's some additional terms that you need to include. If you want to describe I mean, this is just a relatively simple model. You might want to model it in much more sophisticated ways, but the way we're modeling heating and cooling is just by having a linear term in with this sign, it's the cooling. And so the linear term just describes the starlight hitting the medium and heating it. The quadratic term are collisions, so it's allowed to cool. So there's a simple prescription here with the coefficients or the functions. I'll say a little bit how they were adjusted or what they were designed to do. And then the simulations are driven by a random acceleration on large scales, just to drive turbulence, let the cascade develop, and then we're looking at it at late times when it's really stationary. So the simulations that I was looking at that Alexei provided me with are described here. So the 512 cubed simulations, they're multiphase simulations. This has to do with the heating and cooling. We'll see that in the phase diagram. It's also here. The size is about 200 parsecs, so about a scale height, or a bit more than for the galaxy. The mean density is about 5 per cubic centimeter. The magnetic fields are a few microgauss. And then these numbers are somewhat oversimplified because you have different phases, so you might want to break them out. But if you just average over the whole simulation and calculate some averaged Alfvén Mach number, it's around 1. The sonic Mach number is around 5 in the simulations. And then it really depends a bit on which part of the medium you're looking at. The solver I'm not really describing in detail. This is a piecewise parabolic method. The L is for on a local stencil. So this is described in this paper if anyone is interested. And as I said, the simulations were there before Planck. So these parameters are not adjusted to fit anything in the Planck data. They were adjusted to reproduce what's given in the Wallfire paper. So you have a cold medium and a hot medium. You're trying to reproduce those temperatures. And it also, the magnetic fields and so on are consistent with Zeeman observations. It's consistent with Larson's laws, a relation between the size of molecular clouds and their line widths and the pressure PDFs of the cold neutral medium, for which I'm including the reference here. And here's what the simulations look like. If I had known that it's so big, I would have maybe made sure I have higher resolution pictures, but hopefully you still get the idea. So the color coding shows you the column density of H1. So red is a lot of stuff, blue is very little stuff. And then the lines here show you what the magnetic field is doing. This is a projection. Obviously, there's 3D cubes, so this is a projection in a direction that's perpendicular to the magnetic field, which you can see because the lines kind of just walk upwards. So you can see that the magnetic field, on average, just points in this direction. You can also project in the direction along the magnetic field. Looks like this. You see more of the little eddies, less regularity in the magnetic field if you're looking along the magnetic field direction. So then what I was referring to as the dust model is very simple. It's intentionally very simple because I'm trying to highlight that the Planck data really is telling you more about MHD, or the scale dependence, and the E to B ratio is really telling you more about the structure of the magnetic field or the MHD turbulence than it is about the specific properties of dust. So the way I'm defining the Stokes parameters is just that the Stokes I is just the projection of the density. So it's just the column density of stuff. So the more stuff there is, the more it emits. This is obviously assuming that the medium is optically thin, otherwise that doesn't really make sense. I think he's...
So this is sort of the foreground, right?
Yeah. Any questions while we wait, I guess?
Yes.
Yeah?
Suppose suppose you never detect R. What will that tell you about inflation?
Suppose we don't detect R?
Yes.
Yeah, that's an interesting question. So the way we've been phrasing it in the context of CMB stage 4, you can ask, we already know some things. We know what the scalar spectral index is. And you can ask, what are the classes of models that naturally explain the value of the scalar spectral index? So models where you don't have to adjust 5 terms to cancel to get the spectral index that is observed, but something where the functional form is the right form to predict the scalar spectral index. Then in that class of models, you can ask what you learn in that class of models. And so there's only really... you can show it's solving a simple differential equation. There's only really 2 classes of models that are left in that. So there's what people usually refer to as monomial models, where it goes like phi to some power. The power doesn't have to be integer. It could be phi to the 2/3, could be some rational number. Then there's another class of models where you essentially have a plateau that you either approach as a power law or exponentially. And what you're learning from going below 10 to the minus 2, which is what the stage 3 experiments can convincingly do for you, you're excluding the first class of models that I was mentioning, the monomial models. And in the second class, with S4, you're not really excluding the whole class of models, but you're excluding models in that class with a characteristic scale of the potential, so the scale over which the potential varies appreciably, of order m Planck. So this is the kind of reach you have with CMB stage 4. So you're ruling out any model in that class in which the characteristic scale of the potential is larger than the Planck scale. And the Planck scale is a pretty natural target. So that's what you would learn with if you don't see anything. Okay, so then let's get back to the Stokes parameters. And so the Stokes Q parameter is just the density times the y. So this is projected in the z direction. So the only quantities for the magnetic field that are relevant are the y and the x direction. So you have by squared minus bx squared over b squared. So this is a simple model. So this is, you see, that's normalized. So it's just really dependent on the direction, not the magnitude of the magnetic field. This is supposed to model that the dust is perfectly aligned with the magnetic field. If you increase the magnetic field any further, it doesn't really increase how much the dust aligns. So it's just assuming that you have perfect grain alignment. And similarly for the Stokes U parameter, you just have, minus 2bx by over b squared. So this is what you would expect for a very naive dust model. And what you can then do is just take these Stokes parameters, Fourier transform them, and the E and B modes that are usually discussed just given in this way. So there's some algebra you can do, but it just is simple to write down. So if you're trying to get the E mode, you just take this combination. For the B mode, you take this combination. And then you can also compute the power spectra in a trivial way, just averaging over all the directions in, well, actually it's in a plane, so it's not, but there isn't quite true. But so the upshot then is, if you do that simple exercise, the power spectra you find from the simulations look like this. And you reconstruct, or if you measure the spectral indices for the E-modes, you find, depending on whether you're looking at the projection that's along the line of sight, you find something like minus 2.56. The direction that's perpendicular to the line of sight is minus 2.44. You might ask why I'm not going to larger L and why I'm not going to smaller L. So on large L, obviously, eventually, you're sensitive to exactly how you're driving turbulence because you're driving it on large scales. And on small scales, there's numerical dissipation at some point. So the question is exactly what happens as you change resolution. It's not something that we've been really exploring. But so the idea is that there's, it's not much of an inertial range, but there's some inertial range here by, if you're optimistic, an order of magnitude, where you can try to extract a slope that's minus 2.5, 2.4, depending on exactly what you're measuring, which is consistent with what's in the sky. And you can measure the E to B ratio. So again, here you're driving on the largest scale, so you can kind of ignore this point. But the E to B ratio, again, the points are for the projections along the line of sight. This is for the projections transverse to the line of sight. And you see that you get an E to B ratio that is around 0.5, 0.6 with a slight scale dependence. And what I'm showing here was one of the models that Planck had in their paper. So the ratio is slightly different. It's not exactly on top of it, but it's certainly significantly different from one, which was a naive expectation. If you just assume everything is isotropic, then you would have just expected it to be 1, and it's clearly not really 1 in these simulations. So just to look at them in a little bit more detail, if you want to try to understand what's actually going on, it's maybe helpful to break up a little bit more what's actually in the simulation. So this is the diagram of the density versus the pressure, and you see that just, I mean, this is by construction with the heating and cooling, so this is not too impressive, but you have these two phases. So you have a cold phase over here and a warm phase over here. And this is, the figure is weighted by volume. So most of the volume is taken up by the warm phase. Small amount of the volume is taken up by the cold phase. But the emission we saw is weighted by the density. So you might also ask what the density weighted version looks like. If you weight it by the density, then you see that most of the mass is in the cold phase. So it's just small volume, but very dense, and then you have a warm phase that's more dilute. So this is what it looks like, and you can ask, well, what happens if I specifically look at the spectra in the warm and cold phase, because it might be easier to understand them separately if you're trying to understand analytically what is going on. So for the warm phase separately, so if you just threshold on temperature and looking at the warm phase, the spectra look like this. So there's, again, some asymmetry depending on difference between the projection along the line of sight and transverse to the line of sight. And again, the slopes are essentially consistent with what is seen in the Planck data. And the ratio for the warm neutral medium is essentially just flat at 0.5 in these simulations. And the ratio of how much warm versus cold medium there is, you would suspect is different depending on whether you look close to the galactic plane, which is what these simulations are for, versus when you look at high latitudes. So this is also another reason to break it up and look at it separately. Obviously, the way to do it is to really take H1 data, try to understand what the conditions are in the regions you're interested in, and simulate those. And that's something that we'll hopefully do, but we haven't done. So for now, this is a somewhat cheap version of looking at the different contributions. And for the cold neutral medium, obviously, it's dominating. So it's similar to what we were looking at before. So the power spectra are like the ones for the combined thing. So there isn't too much new information here, just because it's by mass dominates, and so the intensity dominates. Another diagnostic I was mentioning was the polarization fraction, or histogram of the polarization fraction. And if you look at this in the simulations, it also looks a lot like what you saw in the Planck paper. So it's reassuring that a lot of these things really come out without any real handle. So again, these simulations were just there before.
On that plot.
Yeah.
The intrinsic CMB polarization fraction, what would that histogram look like if we didn't have any foregrounds?
Oh, if we didn't have any foregrounds. I haven't made that histogram. I don't know what that histogram looks like. It's more polarized than the dust on average, but I don't know what the histogram looks like. It's somewhere over here.
Now, this figure requires some additional assumption about the polarizing characteristics of the dust, not just that it's aligned. So what is assumed there?
I'm really just here plotting what I was saying I wanted to plot, which is the polarized intensity defined from these things here, from square root q squared over u squared divided by I. So that's what I'm plotting here. So the absolute value of the polarization fraction, maybe you shouldn't necessarily look at, or I don't know if one should care, because there should be some numbers here that are in Q and U that are not necessarily there in the intensity. So I wouldn't look at necessarily the scale on the axis, even though they look essentially the same, but I would look more at the shape.
The scale is based on assuming coefficients of 1
Yeah.
in front of those intervals?
Mm-hmm. And so you might somehow wonder if it's specific to this class of simulations. And so we looked at other simulations, isothermal simulations, simpler simulations at higher resolution, and the story goes in a very similar way. So the spectra are again reasonably consistent with the Planck data, and also the E to B ratio is consistent with it. So it's not so clear that this is specific to one set of MHD simulations. So also in these simulations, the B to E ratio is around a half. So in this case, it's pretty flat at a half. And so it really, to me, looks like you're looking at properties of MHD turbulence, not so much necessarily specifically the dust, if we're asking about the scale dependence. And yeah, so this also suggests then that you can maybe, when you're trying to understand it, you might try to understand which modes are actually excited. So that's, I was trying to understand what's actually there, what's making up the fluctuations. And I don't want to go through the exercise of linearizing the equations, deriving dispersion relations. I'm just stating them. So there's the Alfvén modes. If you do the exercise, it's straightforward. So you take these equations, you linearize, you derive dispersion relations, you get the Alfvén modes, which have a dispersion relation that looks like this. And what it tells you is, if you look at the so these, I should maybe have said a little bit more, but I can. So these are transverse, so the displacement is transverse to the magnetic field line. So it's just like you're pulling out the magnetic field lines like a string, which pulls the fluid along with it because of the Lorentz force. And you have these transverse oscillations that propagate. So if you look at the group velocity, you take the omega by dk, you see that the group velocity is just v, which is proportional to the magnetic field. So these are just transverse waves that propagate along the magnetic field lines. Then there's the longitudinal fluctuations, which are generalizations of sound waves, if you want. And there's two of them, depending on the sign here. So they can be, so again, these are perturbations in the density or pressure and the magnetic field. And you can have them in phase or out of phase. The ones that are in phase are the fast modes, and essentially have close to, well, I don't know, it's not entirely isotropic because of this term, but because of the plus, that piece dominates. With a minus sign for the slow modes, you see that there's some cancellations. So they again propagate preferentially along the magnetic field lines. So these are the different modes that you expect to be there in the linearized theory. And you can try to project onto them in the simulations and ask which are the modes that are actually excited. And this is what the mode decomposition looks like. So for anyone interested, the technique that was used is the one that's described here. But so the energy in these simulations at least looks like it's dominated by fast modes. Then there's the alphane modes, and then there are slow modes. And so I think looking at these things, there's some hope that you can actually play with the equations and understand a little bit better why the E to B ratio is what it is, the scaling is what it is, and so on, even though it's not really, obviously not trivial, because it's clearly a nonlinear interacting theory. The last thing we were looking at are simulations with supernova driving. These are by Paolo Paduan. He provided them for us to play with. And so there's an initial phase where there's no self-gravity included to set up the turbulence, and you have stochastic, star formation and some stochastic supernova explosions. And then as time goes on, there's star formation preferentially in the cold regions, and there's correlated supernova explosions in these simulations. The resolution is 1024 cubed in them, and they have a hot phase as well. So the phase diagram looks a little bit different in these simulations. So you can separately look at the three regions if you want. The power spectra, the scaling still roughly works, but they're clearly looking different. So here what you're seeing is that the E to B ratio is essentially, or is close to 1 in these, and the reason, I think, if you're looking at them, is really that supernova just, they inject energies on the scales of interest. So in these simulations, you can't really avoid it. You're always looking at some small bubbles somewhere, which make it somewhat isotropic and ruin the, well, I don't know if it's ruining it, but just it means that if you're looking at the galactic plane, you don't really expect to see an E to B ratio of 2, which you also don't. So it's not bad. It's just something one should study a bit more. But so this is the kind of simulations we looked at. And these are the kind of simulations that I used for the forecasts for CMBS4. So what I did is you just take the MHD simulations, project them onto the sky, and then Brandon helped with the spectral dependence for the dust, and we made a simple synchrotron model. The interesting thing is that also for the synchrotron model, I think there's a somewhat a similar story to the dust. So some of the differences in scaling for the synchrotron just arise because the synchrotron really is sensitive to not just the direction of the magnetic field, but the magnetic field strength. And that really also in the simulations leads to scale dependence and slightly different E to B ratios. But the synchrotron model, I think, is not at a level where you necessarily trust it, because we're really fudging the electron density. So I didn't really include any slides. But the one downside of these models is they're currently limited to small patches. They have high resolution. Changgu here has been working on much bigger boxes where you can make full sky maps of them that we have been using also for the PICO, the NASA probe mission study. They're at lower resolution, so they're good if you want to study something for a satellite on large angular scales, but you can't really right now use them to study much about the recombination peak or the delensing. So that's one of the goals here. And so the goal is to make the two things converge. So we'll meet again in a few weeks here in Princeton to all discuss how to proceed in that direction. Here I just wanted to show that if you put all that into the simulations, you use the sensitivities that we have, or we think we'll have for CMB stage 4, you can remove these foregrounds and recover the cosmic microwave background. What we did notice is that we really, to do that with this model, we needed higher resolution synchrotron channels. So we moved the 20 gigahertz detectors from what were the small telescopes to the large telescopes. It's, I guess, basic intuition tells you the same, but then it's, unless you have numbers that back you up, somehow people are not willing to listen if it changes things. So anyway, so you need high enough resolution for both dust and synchrotron, I think is clear. And so once you have it, you can take 1,000 simulations and see how well you're doing for, let's say, the detection significance for 3 × 10⁻³ And then you see that the median is around 4 sigma after 4 years of observation. So if you have a signal in the sky at around 4 sigma, then obviously there's good motivation to keep running and push it over the 5 sigma detection threshold. But if there isn't anything, so if you're looking at upper limits, then you don't necessarily gain all that much from pushing it down by another small amount. And also here I'm just showing you that the statements when we're saying less than 0.001 at 95% confidence level are somewhat, I mean, they're based on these kind of distributions. So they're really the median of these distributions. So you can be unlucky and be looking at a patch where you don't do as well. You can also be lucky and do much better than you thought you would do. And the same is also true here. Here it's just the sample variance. If at R 0.003, you have a patch that looks like an effective R that's bigger, or you might have a patch that has an effective R that's smaller. So that's why there's these fairly broad distributions for R and why you get these kind of tails. And so this is not what this plot is based on, but if you made a plot based on these, it's somewhat similar, except this actually shrinks a bit compared to the science book. So this was the plot for the science book. We'll update it. And then the upshot is, I think, as we briefly discussed based for one of the questions, that even the upper limits for CMBS4 are interesting for the reasons I already discussed when the question came up. And so just to summarize, so if we're trying to measure primordial gravitational waves, then for the foreseeable future, our best hope is really to look for their imprint in the cosmic microwave background. And the foreground emission in that case looks like the biggest obstacle. It obscures our view of the cosmic microwave background. And we have to somehow deal with it, both to design the experiments, but also then to figure out algorithms that really ideally remove the foregrounds. And to me, it was interesting to see that at leading order, the dust maps really appear consistent with simulations of compressible MHD. So I think the simulations, the data, and some additional theory work might really help you understand why the E to B spectra look the way they do, and might also teach you something about MHD turbulence in the process, and hopefully also will lead to better ways of removing the foregrounds, because clearly these components aren't Gaussian. If you understand them better, there's hope that you can remove them much more efficiently. The MHD simulations that I was showing were really just at a fixed frequency, so then you have to add models for the dust if you want to get something as a function of frequency. And there's also the goal to extend them to really include star formation, radiative transfer, so you get realistic distributions of dust temperatures. That's something we did very much by hand with Brandon. And so eventually, I think it looks like these models can be used for hopefully more reliable forecasts to inform the design, and hopefully eventually to detect the imprint of primordial gravitational waves on the cosmic microwave background. And I'll just end it with that. So thanks.